Alright, so in the last video we talked about current. So in this one we're going to talk about potential difference, and then we're going to look at some laws that current and potential difference have to follow. So let's start off by defining what potential difference actually is. So as charges go through a component, they will transfer some of their energy to it. So potential difference is the energy transferred from each unit of charge passing through a component. So there are two different ways of thinking about potential difference. One in terms of pressure, which helps us understand current, and then the other one is in terms of energy as well. So in terms of pressure, when there's a potential difference across a component, that acts as a pressure to force charges to move through the component, which is why we get a current. And the bigger the potential difference is, the bigger the pressure is for charges to move through, and therefore the higher the current is. Okay, so that's it in terms of pressure. But we also, as we've just seen, think about potential difference in terms of energy. So if there's a potential difference across a component, which we can measure using a voltmeter, that indicates that the charges have changed in energy from start to end. So usually it means they've lost some energy from passing through the component, and it's been transferred into another form, a lot of the times into heat, sometimes into light, lots of other kinds of things. Okay, so let's talk symbol units and how it's measured. So potential difference, the symbol, you'll see me use V typically, or sometimes you'll see delta V for change in potential. And a unit is the volt, which again is given the letter V. So its symbol and its unit are actually the same letter. If we want to measure potential difference, we would use a voltmeter, and we connect the voltmeter in parallel with the component, because essentially what it does is it measures the potential before, the potential after, and figures out potential difference. Okay, so last video we talked about an ideal ammeter, and we said an ideal ammeter has zero resistance. Well, a voltmeter is the exact opposite. An ideal voltmeter has infinite resistance, and the reason for that is we connect a voltmeter in parallel. So we don't want any current to flow through the voltmeter, we want all the current to go through the component it's connected to. And the other thing is, if you connect an infinite resistor in parallel, that has no effect on the overall resistance of the circuit, and we'll look at that a little bit more in the next video when we look at resistor combination laws. Okay, so let's start a look at some potential difference and current rules that every single circuit must obey. So these rules you'll be using as long as you ever study electricity. They're simple but really useful. So these were invented by a scientist called Kirchhoff. He's invented the right word, coined, discovered, whatever you like. But anyway, the current rule: the sum of the currents entering a point, which are sometimes referred to as a junction, where we have two pathways meeting each other or splitting, is equal to the sum of the currents leaving that same point or that same junction. So a really simple example to show you here is we can see in this example we've got current I1 and I2 going into the junction and just I3 leaving. So this law is derived from a much broader conservation law called the law of conservation of charge, which essentially means you can never lose or gain charges. But in this case, what that means is I1 plus I2, which is the sum of the currents going in, is equal to I3, the current going out. Okay, so let's look at a more complex example and something a bit more like a circuit you'd actually see. So this is about as complicated as a circuit as you'll see at this level. This is actually known as a Wheatstone bridge. But regardless of that, regardless of how complicated this looks, we can still use Kirchhoff's current law to develop some relationships and actually see what's been done wrong with this diagram. Okay, so first of all, we can say that I1 is equal to I3 plus I5, because at the junction on the left-hand side, I1's going in, I3 and 5 are coming out. So we know that that must be the case. So it's a complex circuit, we've got a simple relationship. We do the same thing at the other junction on the right. We've got I2 and I5 and I4 all going in, which must mean that as there's nothing coming out, they must sum to 0. And that might look a bit odd, and this is why I said we'll be looking for a mistake, because what this tells me is that we've got one of the currents in the wrong direction. So maybe it's I5, maybe it's I4, but I reckon it's probably I4 in this case, because we need a current to be coming out here. But again, all the Kirchhoff's current law does is take a complex circuit and analyze it bit by bit in simple terms. Okay, so now we can talk about Kirchhoff's other law, his law of voltage or law of potential difference. So what his law states is the sum of the EMFs, which I'll talk about in a second what that is, in a complete loop or complete circuit is always equal to the sum of the potential differences. So EMF is associated with power sources. So EMF is the energy given to each charge that passes through a power source. And remember, potential difference is the energy transferred from a charge as it goes through a component. So EMF and potential difference are essentially the opposites of each other. EMF is giving charges energy, potential difference is kind of taking it away. So this law that we've got, the sum of the EMFs is equal to the sum of the potential differences, is a law of conservation of energy. And what it's basically saying is any energy you put into your circuit, there must be a device taking it out. That's what it's essentially saying. So EMF is given the symbol epsilon, which you get in the Greek alphabet. And it has the unit the same as the potential difference. It's the unit of a volt because it's still energy per charge. Okay, so let's have a look at a couple of examples of this in use. So in a simple series circuit, so what we've got is we've got a cell that's providing an EMF, and I've just given it a symbol. We're not going to give it a value. And we've got two resistors with potential differences VA and VB. So Kirchhoff's voltage law tells us in this case that the sum of the EMFs is just going to be this epsilon value. The sum of the PDs is going to be VA plus VB. So what his law tells you is that those two things must be equal to each other. Okay, so that's a simple example. What about if we have them in parallel? Well, this is where the little term in Kirchhoff's voltage law about complete loop becomes important. So I'm going to show you the loops in this circuit. So generally with loops, we go from a power source and back to the power source. And there's several pathways to do that in this example. So one possible loop is this one here, going through resistor A. Okay, so in that loop, the sum of the EMFs is the same. Sum of the PDs is VA. So Kirchhoff's voltage law tells us VA must be equal to the EMF of the battery. Now let's get rid of that loop and add in a second loop that we've got here. So we've got going from the power source through B and back to the power source again. So again, we can do the same process and we figure out that VB must be equal to the EMF of the battery in this case. So given that the EMF is the same in both, what we can conclude is the potential differences across these parallel resistors must be the same, and in this case they're equal to the EMF of the battery. Okay, so let's have a look at kind of the most complicated kind of example you'd be using this for. So let's again start off drawing a loop. So this loop, I'm going through resistor A, you have to go through C and then back to the power source. So again, same process, sum of the EMFs, sum of the PDs, that gives us an expression using Kirchhoff's voltage law. Do the same thing again, let's go with a different loop, this time going through B. Again, same process, and we get an expression for Kirchhoff's voltage law. So now in these two expressions, we know the EMFs are the same and the potential difference across VC are the same. So we actually end up with this same expression, potential difference across A and B are the same, and any two resistors in parallel, that will always be the case. And once we figured out what the potential difference is across either A or B, if we add that to C, that should give us the total EMF. Okay.